And next, we're going to go into a bit about gravity, because gravity connects with uniform circular motion very nicely when we talk about orbits. So a little bit of history. So one of the early thoughts of gravity was related to Aristotle. He gave us lots of things to believe in, like the natural state of an object is at rest, as opposed to an object in motion tends to stay in motion. He gave us the four elements: earth, water, wind, and fire, and the fact that the Earth is the center of the universe, I believe, not just the solar system, but the universe, the geocentric view. But I mean, you got to give the guy a break. It would be pretty difficult to figure out that we were moving and everything else was moving too. Um, so it doesn't feel like we're moving. So I could see where he's coming from. But they did have to come up with some interesting explanations. The other planets appeared to be doing loop-de-loops. If they were just going around us, if the Earth was stationary, then the other planets were doing loop-de-loops, which they called epicycles. So they had a cycle and then an epicycle as it traveled around. Galileo is experimenting with the early telescope, and he discovers that there are four satellites of Jupiter. And suddenly that's interesting that he can tell that these moons are orbiting Jupiter. So if these moons are revolving Jupiter and not the Earth, maybe the Earth is not the center of the universe, and maybe Aristotle is not correct. The Catholic Church did not take kindly to this. This was during the time of the Inquisition, and they persuaded him to change his views under who knows what kind of threats, probably death. But he is spared. He recants his views and says that they weren't true, but he's placed under house arrest for the rest of his life. The Catholic Church did kind of apologize. A few years later, 1979, Pope John Paul II said Galileo may have had divine inspiration, and that's how he realized that Aristotle was not correct. There was a brother, a well-to-do man named Tycho Brahe, and he takes these meticulous measurements of the movement of the planets and the stars in this around 1600. He gathers all this data, but he believes in a geocentric model. He believes in Aristotle. As a side note, Tycho apparently had a disagreement with another gentleman, and they solved things the way you solved things back then. You had a duel, and he got his nose cut off in this duel. And he had one made out of metal that he would use paste and glue on. That had to not be distracting to talk to him with a metal nose. But Tycho had an apprentice, Johannes Kepler. You've probably more likely heard of this guy. He had access to all of Tycho's data and helped collect it, I'm sure. He believed in a sun-centered world, so he was able to make more progress than Tycho did. So from analyzing all of this data, he comes up with 3 laws of planetary motion. One is that basically the planets travel around the sun with in an ellipse, in an elliptical orbit, with the sun at one of the foci. And so that's the first one. They're not in circles. They're in ellipses. The second one he came to the conclusion of was that as they travel around in these elliptical orbits, the planets or anything that orbits the sun, the asteroids or whatever, they trace out equal areas in equal times. So, for example, the Earth speeds up when it's close to the sun and slows down when it's further away from the sun. So as it speeds up, you get a larger arc, but the radius of the arc isn't as big. So as it slows down, you get a smaller arc, but the radius of the arc is larger. So the area of all of these individual little frames is the same. So just showing a very highly elliptical orbit. So Here you again have it doesn't travel, it's not traveling very quickly here, so it traces out a small arc. And here it's traveling much more quickly. It travels a larger arc, but it has a smaller radius of the arc. So the third thing that he comes up with is this mathematical law, and that is that the ratio of the square of the periods of any objects orbiting the sun is equal to the ratio of the cube of the radii at which they orbit. And we're going to use this equation very, very basically. This isn't a big equation for us. I'm just kind of throwing it in here. So we're going to use very simple math with this. We're going to use for the radius, we're going to talk about things in terms of AUs, which is an astronomical unit, which is the distance between the Earth and the Sun, which is about 93 million miles. And we might as well talk about convenient periods. We'll talk about periods in years. So we've got an asteroid that orbits the sun at a radius of 2 astronomical units. What is the period? Well, we're going to make A the top object, the asteroid, and we're going to make B the bottom object, the Earth. So we're going to have the period of the asteroid squared over the period of the Earth squared, and the period of the Earth is one year. That equals the cube of the radii of them. Now we're going to say that the radius of the asteroid is 2 astronomical units cubed, and the radius of the Earth is 1 astronomical unit. And if you do the math, we get that the t equals 2.8 years. So it would orbit at 2.8 years. That would be its period of orbit. Now, Kepler's laws were only laws. They were not theories. If you remember from possibly freshman year, that's because laws tell you what to expect. Okay? The period of this asteroid will be this. It doesn't explain why. We know that the planets orbit the sun, but we don't know why. And along comes Newton, and that was that's where we really start making some headway here. So, are you attracted to the person sitting next to you? Physically attracted? The answer is yes. You have a physical attraction because you have your own gravitational field, and that was discovered by Newton. You have your own gravity. So Newton was a stud, came up with the 3 laws of motion, his 3 laws, invented calculus more or less. Of course, he had help. He read other people's work. But anyway, he did all this in his 20s. He was a stud. The story goes that he's sitting by an apple tree, and an apple hits him in the head, and he wonders if the force that pulled the apple to the earth wasn't the same force that pulled the moon and keeps it in a circular orbit around the earth. So Newton knew that the moon was changing velocity because it was constantly turning. He knew that there had to be a force acting on the moon, and so Newton is thinking that, hey, maybe the force of gravity from the Earth, maybe it can make it all the way out to the moon. This is against what other people thought. People thought that there were certain laws of physics that applied to the Earth. Because we were flawed individuals, and we had, these we were drawn to the earth, bound to the earth because we were flawed. And the heavens had they were perfect, and they had a separate set of laws. Newton says that's not the case. Maybe the Earth's gravity can pull all the way out to the moon, just like it pulls on us. So now Newton has to do a little bit of work here to see if he's correct. So he figures, okay, you knew that the apple was 1 Earth radius away from the center of the Earth. He also knew that the moon was 60 Earth radii away. How they knew this, I did not know. But he knows that the moon is a lot further. So he figures that the the gravity is going to be weaker with the distance squared. So he figures that it should be 160 60th squared should be decreased by that amount. So he matches the Earth's or the Moon's orbit, and it does match his ideas that it is with 60 squared. So he basically knows that the force of gravity between the Earth has to do with something divided by the radius squared. He figures, okay, so since a 2-kilogram object has twice the mass, it also has twice the weight. It's got to be proportional to the weight of the object that we're interested in measuring the force of gravity on. Newton thinks back to his own third law of motion and said, well, if the Earth pulls on the apple must pull on the Earth too with an equal force. So there's got to be a force. The mass of both of those has to come into play. And he puts this together in Newton's universal law of gravity, which is that the force of gravity is equal to this big G, which is a fudge factor, times the mass of the first object times the mass of the second object divided by the distance between their centers squared. So, and that is important. It's from their centers squared. So, we're talking about planets and stuff like that. It's not that big of a deal. But if the objects are closer, it becomes a bigger factor. So, now what is G? That we'll come to in just a second. So if we have two objects M separated by distance D, there's a force F between them. Okay, what's going to happen to that force if I double the mass of one of the objects? I'll double the mass. Well, it'd be twice the force. It'd be 2F. What if I double the mass of both of the objects? Okay, that would be 4F. It'd be 4 times the force. If I doubled one and tripled the other, would it be 5F or 6F? It'd be 6F because they're being multiplied, not being added. And if we had M and 3M, it'd be just 3F. Okay, now let's talk about what happens if we change the distance. Now, not only is it divided by the distance, it's divided by the distance squared. So we've got our same MMDF. Okay. Now what I'm going to do is I'm going to double the distance between the two objects. So I'm going to double this on bottom. Well, it's going to square, so it's going to be divided by 4. So it'd be F 1/4 F, or F over 4. What if I have the distance between them? Okay, so if I divide by 1/2 squared, what is dividing by 1/2 squared? That's 4 times, so it'd be 4M, or 4F. What would happen if I doubled the mass of both objects and doubled the distance between them? Well, doubling the two masses is going to multiply it by 4. Doubling the distance is going to divide it by 4. So it's a wash. There's no change. So this is Newton's law. Now, we don't know what G is yet. G is a fudge factor, a number, just to make all the other numbers work out, because there's no fundamental reason why these numbers should work out. I mean, we just came up with an arbitrary unit amount of mass and called it a kilogram. Came up with an arbitrary distance and called it a meter. So how should this all work out? Well, all you have to do is take a couple masses, known masses, measure the distance between them, and measure the force, and then solve for G. You just need to measure everything else. You need to know the two masses, the distance, and the force between them. Okay, well, that's easier said than done. If I take 2 kilogram masses and I put them, let's make the math real easy. We'll take two 1 kilogram objects. We'll put them 1 meter apart, and then I'm going to measure the force of gravity between them. What's going to be hard about that? Well, the force of gravity between them is going to be so small I can't measure it. It's going to be really, really hard to measure. But along comes Henry Cavendish, a very eccentric guy. Did scientific research as his hobby. He was terrified of women. He had a separate set of stairs made for the female servants to use, so he never ran into them. And he only communicated with his female servants by notes, just terrified of them. and apparently dressed old school even for the time. But anyway, it was a smart gentleman. He comes up with this way of measuring the very, very weak forces. So he comes up with this bar with two masses on it, okay, suspended by a thin thread or fiber, with a mirror on that fiber, um, and a light source. So what happens is he takes these two masses away, and this should read at 0. Okay, he puts the two masses near. Okay, this metal bar pivots ever so slightly uh, against the resistance of the thin fiber. It doesn't take much force to twist a fiber, and that's what he used to measure the very, very weak forces. So as the fiber twisted, this mirror pivoted, and then the light beam from the light bulb would move on this scale, and he was able to calculate the force. And so he figures out what G is, this big G constant. Um, and with everything else known now, they know that 9.8 newtons is the force of gravity on a 1 kilogram object. With this radius away from the Earth, they're able to figure out the mass of the Earth from this experiment, because now they know everything but the mass of the Earth. And this is often called the weighing of the Earth experiment. So you do not need to memorize this, but they've calculated the mass of the Earth is 5.98 times 10 to the 24th kilograms. Do not need to memorize that. I will, of course, give that to you. Now, so what you do need to know, though, is that G is equal to 6.67 times 10 to the minus 11th. And that is, what is it, meters squared per Newton, meters squared per kilogram squared, something like that. There it is, square per kilogram square. And so you can program that into your calculators, by the way. If you've got a graphing calculator, type it in and then hit the STO button, the STO button. If you've got a TI, it's on the bottom left. And then hit alpha and then G. And so it should say ANS, or it should say 6.67 times 10 to the minus 11th. Then there should be an arrow to the right and then a G, and then just hit enter. And now you can type in G instead of having to type in 6.67 times 10 to the minus 11th. Handy to know. So why does gravity get weaker with the square of the distance? Okay, well, there's a lot of things do this. Sound, light, magnetism, anything that kind of radiates out in a sense. So if we look at a light bulb, and let's say it's in a sphere, it's in a hollow sphere, there's a light bulb in the middle. There'll be a certain amount of brightness on the inside of this. Okay, if I double the area of that, or the radius of that sphere, if I double the radius, the area inside is going to increase with the radius squared. So the inside will be 4 times as great, which means the light will be spread out over an area that is 4 times as vast, and therefore the light's going to be 4 times dimmer. So there's also the book used to use this analogy of a butter gun. So if you picture, this is 1 square of toast, this is 4 squares of toast, this is 9 squares of toast. The spray of that increases the area over which it spreads with the distance squared. So gravity does this, light does this, sound gets weaker with the distance squared, magnets, radioactivity, all these things do. You can think about it as expanding bubbles. Increasing with the distance squared. So what is the force of gravity between the Earth and the Moon? Okay, based on their average distance and that kind of thing. So F sub G equals big G m Earth times the m of the Moon divided by the distance between them squared. So this is just a plug and chug. I recommend that you try doing this and seeing if you get the right answer. You should get 1.99 times 10 to the 20th newtons. If you mess up, what you probably are going to mess up is not putting this distance in parentheses. So put this in parentheses and then square on the outside of the parentheses. So if you mess up, that's probably what you did. Now, which object feels the greater force of gravity? The Earth on the Moon or the Moon on the Earth? The same. Okay. This used both the mass of the Earth and the mass of the Moon to figure out the force of gravity between them. There's an equal force. Newton's third law says the force of gravity is the same between them. Which would have a bigger impact on the force of gravity between them? Doubling the mass of the Earth or doubling the mass of the Moon? It would be the same. If you double the mass, okay, you're going to double the force of gravity between them, no matter which one you double. Trick question. Okay. Okay. So what is the force of gravity, let's say, between you and your neighbor? Let's say you and your neighbor are both about 70 kilograms and you're at about a half a meter apart. Again, I would probably suggest trying this. The force of gravity between you and your neighbor is about 1/1,000,000th of a Newton. So if you were to take an apple, cut it into 1,000,000 pieces, and feel the weight of one of those pieces, that's equivalent to the force that's between you and your neighbor. One more example, bear with me, and we'll get through one more example, then we'll call it a day. So what we want to figure out is based on Newton's universal law of gravitation, what is the acceleration of an object near the surface of the Earth that's falling? So we're going to have an object mass m, that's going to be u or whatever. We've got the mass of the Earth. We've got the radius of the Earth. Now, since we're at the surface of the Earth, you're going to use the radius of the Earth because that's the distance from the center of the Earth, and that's the distance that you use. So what force is going to be? It's going to be big G m over r squared. Okay. So the force of gravity is going to be that on you. So this is also going to equal your mass times your acceleration. Your mass times acceleration is going to equal your F times G, okay, if you're dropped. So which is equal to Gmm over r squared. Now your mass is going to cancel out, okay, and what's left is going to be the mass of the Earth. Okay, so if you plug in all these numbers, big G, the mass of the Earth, the radius of the Earth, you get that the acceleration of an object near the surface of the Earth is 9.8 meters per second squared. That number sounds familiar. I did this to show you that Newton's gravitational universal law of gravitation works everywhere. Okay, force of gravity equals mg. It works at the surface of the Earth. That is a special case. Newton's law of gravitation works everywhere. It works between black holes, comets, and anything you can think of. And that's where we'll end today.